Let's continue our exploration of some of the other continuous distributions. A joint distribution of two variables is called a bivariate distribution. Bivariate distributions may be discrete or continuous. The variables may be independent, or there may be a covariance between them. A special case of the bivariate distribution is the bivariate normal distribution, in which there are two normally distributed random variables. When seeking to understand the life cycle of products, the exponential distribution can be very useful. The exponential distribution is closely related to the Poisson distribution. If a random variable x is exponentially distributed, then the reciprocal of x follows a Poisson distribution. Because of this behavior, the exponential distribution is usually used to model the mean time between occurrences, such as arrivals or failures. The mean and standard deviation are 1 over the failure rate, or lambda. Often in statistics, we are faced with a distribution of data that is not normal. We have the ability to transform this data using any number of fractional exponents or logarithms. If a data set is known to follow a log normal distribution, transforming the data by taking the logarithm yields a data set that is approximately normally distributed. We know that when random variables are summed, as the sample size increases, the distribution of the sum becomes a normal distribution regardless of the distribution of the individual data. Since log normal random variables are transformed to normal random variables by taking the logarithm, when random variables are multiplied, as the sample size increases, the distribution of the product becomes a log normal distribution regardless of the distribution of the individual data. This follows from a common rule in math, which states that the log of a product is equal to the sum of the logs. The log normal distribution takes on several shapes, depending on the standard deviation. The log normal distribution skews to the right as the value of sigma increases. A scale parameter, the median, is partially used to control the shape. The equations for mean and standard deviation are given here, where mu and sigma squared are the mean and variance of the natural log values. The Weibull distribution is one of the most widely used distributions in reliability and statistical applications. It is commonly used to model time to fail, time to repair, and material strength. There are two common versions of the Weibull distribution, the 2-parameter Weibull and the 3-parameter Weibull. The difference is the 3-parameter Weibull distribution has a location parameter when there is some non-zero time to first failure. The PDF for the 3-parameter Weibull is given here. Beta is the shape parameter, theta is the scale parameter, and delta is the location parameter. The shape parameter is what gives the Weibull distribution its flexibility. If beta equals 1, the Weibull distribution is identical to the exponential distribution. If beta is between 3 and 4, the Weibull distribution approximates the normal distribution. The scale parameter determines the range of the distribution. The scale parameter is also known as the characteristic life if the location parameter is equal to 0. 63.2% of all values fall below the characteristic life, regardless of the value of the shape parameter. The mean and variance of the Weibull distribution are defined here in terms of the shape and scale parameters. Note that the gamma function is also deployed in these calculations.